This is my first time recording I guess an online tutorial. I hope you learned something from it, but it's really to help me sort of get my head around using JavaScript. Recently I've been working on a range of little tasks and puzzles set by Exercism, which is an open source platform and website for learning various programming languages. I've been focusing on JavaScript, and today I wanted to talk about my approach to solving one of their, I think, relatively simple challenges, which is related to encoding and decoding strings. I'll flip over to their website where they have a description of the puzzle here. Put simply, this is one of about 150 various little puzzles that you can do on JavaScript inside Exercism, which is a fantastic platform, and I've really been enjoying using it. I've even used a mentor, or had the help of a mentor at one point to help improve a solution, or help me get to a solution for a puzzle I was working on. This particular one is about ciphers. There's a few parts to it. There's an introduction here talking about probably the simplest type of cipher, which is the Caesar Cipher, where basically you shuffle the letters of or the characters that make up your message. You shuffle them over by 5 or 10 or however it's set, so that you get what looks like a bit of a scrambled sequence of letters, a nonsensical sequence of letters. We're going to practice building a program that can do that, that can even take a key and encrypt a string here. There's a discussion here about how if you have a string and you're doing a substitution cipher, if you have a string of all A's, it doesn't actually transform the message, because the index position of A in the alphabet is at 0, and so that there's nothing to change. If it was D, however, everything would be shunted over by 3 characters. So I shifted up by 3 characters, J, K, L, okay, and likewise A goes up sort of by 3 characters, to B to C to D. And so then that's kind of the simplest. It's one step along from the Caesar cipher, because you can have a key that varies along this sequence now, instead of just fixing the shift value by some certain amount. And then the discussion here also mentions that human beings are not very good at coming up with randomness, and so it would be neat if you could instruct your program to generate a long key. They suggest 100 lowercase characters in length, use that for encoding and decoding. You can go on and read more about key exchange protocols, which is interesting as well. Let's move on to the program that I wrote. I think it's pretty simple, and I'd just like to take a couple of minutes to talk about why I built it the way I did, and this might provide some food for thought for others that are working on this puzzle or something similar. Open to criticism, suggestions. I'd love to hear about creative solutions that other people have come up with for this puzzle. I'm a bit of a newbie, so forgive me for some of the shortcomings that might be in here. It does pass all the tests that were required, and I hope I've made a reasonably sort of sensible choice in the way I've built it. Anyway, we'll get started. The code that I wrote is a class called Cipher, and it can take it can take a key if you specify it, If you don't specify a key, then it'll generate a random one here, and that's in the 100 character format that was dictated at the end of the challenge. I'll come back to this generating a random cipher bit later on, because it was a little bit further along in the description of the puzzle. I assign the key to this, I think it's called a getter, to make it a little bit, I think it's a little bit less available for tampering, I think. It more secure to do it this way. It does mean that later on I have to include this this method for getting the key and retrieving it from this underscore key. We'll just skip over now for now the way I generate the random cipher. But before I do, I just wanted to mention that later in the program I'll be referring to the character codes of the characters that make up the input string and the key. The ASCII codes, character codes for lowercase alphabetical characters run from 97 through to 122. So let's move forward to how I encode an input here. This is a method, encode, and we accept an input. Because we're using ASCII character codes, and sometimes these, in the course of this program we'll come across it in a moment, these are shifted around. Sometimes the result can sort of carry you beyond sort of the range of the characters A to Z, in which case we would expect or we would like the program to go back to the start of the alphabet and continue that way. For instance, if we're encoding the character Y, and the key at that index position is a B, we want to increment that by sort of 2 index positions. So we go from Y to Z, then we want to come back to A. So basically we need a way to normalize the character code. So if we go sort of one beyond the range we're working, we want to loop back to the beginning. So that's why I include this program here. This function here inside our program, which is for normalizing the character codes. So we'll refer to that later in this method. So because we're doing an encoding, we want to eventually return an encoded message, and we initialize that as an empty string, and then we set up a for loop to basically iterate over each character of the input and encode those as we go. We track the key index, or we can't translate necessarily directly the index that we're using for looking at characters in the input string. We can't necessarily use the same index when we're referring to characters in the key, because the key can be shorter and often is shorter than the encoded than the input. So we kind of wanted that to be looping over and over as well. And so we accomplished that by assigning a variable or assigning a constant here. The key index is the index number of this loop, which corresponds to the index position of the input message, and then we take the modulus of that, which is the length of the key that we're using. So if we have a key of only 3 characters, and I is 3, so we'd be looking for the 4th position of the key. We'll divide by, we'll take the modulus of that, where in this case the key length would be 3, so the modulus would be 1, and then that would, sorry, I think I got the numbers there wrong. Let me zap that, and I'll and do that again. So we're going to take the modulus. So if we've got a 3-character key, and we're at index position, index number I equals 3, it's as if we're looking for the 4th character in the key, but we want to go back to the beginning. So when we say I is 3, and we are dividing, taking the modulus of that. That will, and the key length is also 3, then the modulus will be 0, and then that key index of 0 corresponds to the first character of the key again. So it's just a way of cycling through the key there. We set another constant here, which is a cipher shift, which is working out how for each time we refer to the key, we want to know how far to, or how many characters through the alphabet to increment our input, and to calculate that, we just look at what the character code of the key is at the key index, calculated from the line above, and we subtract 97. So because 97 is where the ASCII code numbers commence for the letters of the alphabet in lowercase. So if we had a key index here, sorry, if the character code was for B, it was 98. We subtract 97, so our cipher shift would be 1, and would be increasing the we'll be going from B to C, or from D to E when we go to shift the cipher character code, and that's what we accomplish here by looking up the character code at our index position in the input, and then adding whatever that cipher shift value is from above. We can now calculate what the encoded character is for that position, and we do that by taking our cipher character code. So we've shuffled along however many we're meant to go in the alphabet. We normalise that character code because, as I mentioned earlier, we might be outside the window of lowercase alphabet letters within the ASCII system, and if that's the case, we want to kind of wrap around and come back into that range. So we normalise, and then we want to produce a string, so we want the actual letter that we can add to our encoded message, and that string is drawn from the character code, the ASCII character code, which has been normalised and which we've obtained in that loop. We concatenate the encoded character into the encoded message, and then this loop will continue until we've assessed every character in the input, and then we will return the encoded message from that method. That's encoding. Decoding is very similar, so I'll move through that quite quickly because it's kind of the reverse. We still have this function here for normalizing the character codes for the same reason. We initialize the decoded message as an empty string, and then we loop through every character in the encoded message and shift each character back by the right amount. So we read the key at that the correct position, and then we subtract the cipher shift here instead of adding it like we did in the step before, because now we're decoding, and then we normalise the character code in case the result of that has taken us outside the range of ASCII codes for lowercase alphabetical characters, and then we generate a string from that ASCII character code and concatenate that with our decoded message string, and then after this loop has iterated across every character in the encoded message, it will exit and return a decoded message. So that's the encoding, the decoding, and the only other thing I wanted to touch on was the generation of a random cipher. I've set it up here so that when you're constructing a cipher, you can specify, the key can be specified, but if it isn't, then this function will apply, whereby it will generate a random key. I've set the cipher length here as was specified in the instructions for this puzzle, at a key length of 100 characters. And to generate this, the random cipher, I initialize that as an empty string. I set a range here, basically by specifying the minimum character code, which is 97, the ASCII code for A, and the maximum character code 122 is the ASCII code for Z. I loop. I've create a loop here, which will run as many times as specified in the cipher length, and it will come up with a random character code set basically to what it uses a random number and picks from the range that we specified, and then it picks from the range that was specified and is rounded down appropriately, and then that character code is converted back into an actual alphabetical character using the method and class here, and incrementally added to our random cipher. And once we've looped, this loop is completed as many times as we specified in the cipher length, it'll close and return us our random cipher. So that's how I put the code together. There's a range of tests here that I needed to satisfy. When I was building it, I'd slowly release these as and then test and then iterate and improve the program and keep passing them as I go along, which is kind of fun to get another one passing as you work along. Basically, there's a few parts here. First of all was just making sure that it could encode, can encode, can decode, is reversible. You can encode something and then decode it, and you'll get the same text back again. So your methods are reversible, and there's also a test here using some regex to ensure that the key that's being produced is only made of lowercase letters. And here's the method key, which institutes the getter that I'd set up as well. These subsequent tests get a little bit more challenging. There's a key here that a substitution key that is applied. If we encode a string that is all A's, then it should return the key itself, because the index value of each of these characters is 0. So when they don't modify the key, I guess you'd say, and so you get the key back. Likewise, if you try to decode a message, which happens to be the same as the key, then you'll get all A's back. So it tests that that's the case. It tests again that the function, that the methods when applied in sequence will work as expected and reversible. Can you encode something that for which the key is the same as the input, and if you do, you should get this output. Yes, that's the case. Can you wrap on encoding? When these letters are encoded, if you increment Z, so the index is say 25, and you increment it with I, whatever it is, 9 or something, then you're gonna end up outside the range of 0 to 25, and this is basically testing to see if you can wrap, and in decoding as well. So are we normalizing the character codes, and that's testing for that. So that was why that had to be included. Can we encode messages that are longer than the key? So basically asking do you wrap back to the beginning once the key is exhausted during encoding and decoding, and that's why I had to include a little bit of detail for accomplishing that as well. So those are all the tests that were specified there, and I tested these work by running the npm test on the command line. So I'll just hit that now, and you can see there that it passes a 12. And when there's no red up on the screen, then it's a little bit of a celebration. So that's the most recent little puzzle I've been working on, and I'll keep chipping away at the others. I feel like learning JavaScript is like a little bit like learning another language, and that I just need to use it every day, and try and be a bit more fluent with it. But I highly recommend Exercism for learning programming language. At least in my experience, it's been very helpful, and there's a great community around it, and it's a bit of a sidetrack for me while I've been working on the Odin project, up to the intermediate JavaScript section there, and I felt like I needed a little bit more sort of practice and background to using JavaScript, so that's why I've been spending a bit of time on Exercism. Both great projects, and I might do a few more of these, because I think it's helpful to talk about what I've done and why I did it, and hopefully it makes it clearer in my mind. And if anyone helps, if this helps anyone else, then that's great. And if you have comments, they'd be very welcome. So I'll close it there. Bye for now.